Hello, my name is Alves, and I am a visiting teacher in the Polytechnic Institute of Correia. And I will present the paper with name eHealthCare, a medication monitoring approach for the elderly people.
This presentation have 5 important points. The first point, the first section with name, context, and motivation, where it makes a small introduction to the problem, the challenge faced for the solution of the problem, and a brief description of the architecture built. The second section with the name similar approach, where is detailed some points on existing approach into the market. The next section with the name architect is where a brief introduction is made to the built architect. Section 4 and 5 describe the implementation and conclusion respectively. Tolerance to medication is unfortunately quite common, especially among patients with chronic disease and the elderly people. This tolerance is usually associated with factors such fear of the possible related effects, mistrust, and other problems. Depending on the chronic disease in question, the incorrect medicine ingestion likely becomes a problem for the patient health. Identifying if whether the medication was taken correctly in many cases is an extremely complicated task. A good example of this difficulty is the case of the schizophrenia, where there are patients who can survive treatment failures for considerable periods without adverse consequences. There are many factors which is necessary to take into account to build a tool that can help detect no adherence of the medication. First fact is the purpose of this tool is to help older people, where often there are difficulties in the use of the technologies such as mobile phone and a computer. The next fact is on the side of the institutions that provide services in monitoring medication, it is necessary to create intuitive user interface since the presence of the IT technicians will hardly exist. The last fact is the operation of the tool should require as little human intervention as possible, avoiding that institutions have to allocate human resource to work especially with the tool. Other challenge that is also necessary to analyze is in the field of technology. First challenge. The tool built in the context of this paper is intended to be implemented in low density regions, where sometimes support for internet-based communication is not possible. As the tool was idealized by mode, that is an installation by each institution, its construction has to be thought to the point of not need very expensive physical resource. Although the NB-IoT network already has a good worldwide support, in some regions it's not yet possible to use it, which has led to creating an alternative communication solution for areas where support for NB-IoT does not exist. Based on the challenge described in the previous slides, it's increasingly necessary to design tools that provide a new solution for the monitoring of medication. The eHealthCare is an approach to allow to identify possible users who do not adhere to medication, using for this a small set of sensors, chips, and artificial intelligence process. Our solution responds the necessity of the market to the new solutions for the monitoring of the medication. Inside the section with name similar approach, we have a lot of the points to discuss. So the development of solution to help identify no adherence to the medication is not something new in the market. There are a lot of the solution. For instance, peel back, tape timer, it's on. Despite eHealthCare has similar functionalities to other solutions in the market. It's important to clarify that its target audience is different, okay? So while solutions similar are targeting for any user who needs medication, our solution is aimed at institutions and was conceived as a monitoring and control solution for the detection of the medication no adherence. Because of the difference in target, we choose not to perform a comparison test between similar approach and our tools. Based on everything that was being said until now, our solution is composed by 5 components. First component is a web server that provides a set of endpoints used by the mobile application and the administration port. The second component is a broker who will be responsible for managing the exchange of the message between the web server and the Arduino board inserted in the organizer of the medication. The next component is the medication organizer adapted to the users which have a strong rejection of the use of technologies. A set of the intelligence process is the next component available through the Flex framework that will be responsible for identifying users who are not adherent to the medication. The last component is the mobile application and the administration portal. This slide contains the global view of our architecture. The component more or left is the part will be installed in the institution. This part is composed by 2 components, the portal and the mobile application, and both will help to make the management of the medication organized. More at the center, okay, there are a web server and database server, and both are responsible for connecting all components to its endpoints. In the center is also represented the intelligent system that will give the probability of a new user being no adherent. And for last, the broker that will communicate with the organizers. On the right in the picture are the organizers that will be described on the new slide later. As mentioned above, the web server component is the point of connection between the multiple components of our architecture. These components are intelligent system, field organizer through the broker, administration portal, and mobile application. This application server, using the Java language, contains the set of the web service and the web page necessary for the operation of the tool. In addition to the servers, it contains a set of the additional timers and services to interact with the intelligent system in order to pass on the incoming data. The next component to present is the broker and the Arduino board. A broker, as mentioned above, is who will be responsible for managing the exchange of the message between the web server and the Arduino board. Thus, the MQTT protocol was used, which through a broker that managed the exchange message. It guarantees guarantees the communication between the web server and the Arduino board in both directions. Although Arduino board is able to communicate using NB-IoT, broken was necessary because on the web server side, there may be a need to send messages to the organizer. For instance, when institutions unlock organizer. This is the organizer build. In short, it's delivered to the user already containing all medicine and their schedules. The empty slot does not contain protection. So when it is detected that a user was to take a medicine, the slot that corresponds to the taking is rotated and placed in the empty slot. In parallel, a sound is emitted to notify the user. The user was 20 minutes to remove the medication. After this time, Arduino board sends to the server the information if the user take or not the medication. The eHealthCare intelligent system is composed by two components: the address controller and classification model, as shown in the picture below. The address controller is responsible for controlling the rate of the non-adherence to medication of the patient of the eHealthCare system. The classification model is responsible to classify the level of the non-adherence to the medication of a new patient. For the usage of the intelligent system, two metrics were associated to the patient. First metric is the level of the non-adherence to the medication, and the second is the rate of the non-adherence to the medication. The levels of the non-adherence to medications is classified in four levels. The first level is the level green, and means the patient is rarely no adherent to medication. The second level is the yellow level, and means the patient is sometimes no adherent to medication. The next level is the level orange, and means the patient is no adherent to medication with some frequency. And the last level is the red level, and means the patient is totally no adherent to medication. The level of the no adherence to medication is used in the classification and to monitoring the rate of the no adherence to medication. Another value had for usage of the intelligent system was the effect in the rate of the no adherence to medication of every medication. This value was added because the effect of the not consuming some medication is greater than other medication. All values mentioned are key elements to the operation of the adherence controller. The adherence controller has two processes that are always running. The first is waiting for the data sent by the Arduino, but forwarded by the HTTP server when a patient does not consume the medication. The second process runs periodically once per week. In this way, one trigger, the first process is going to update the no adherence rate of the patient in question, adding to that value the effect of the specific medication times, the number of the consecutive days that the patient is no adherent to medication. The second process runs once per week and will update the no adherence rate of the patient that have consumed the medication without any failure in the current week, reducing that value by 5%. If this update changes the level of no adherence of the patient, the classification model that will be discussed will be trained with the update data. Since the adherence controller is training the model every time, the level of the no adherence of the patient changed. There was a need for a machine learning algorithm that could be fast and computationally light. In addition, that machine learning algorithm needs to be a supervised machine learning algorithm, since the authors add labels data to training. and solve a classification problem. Size, the objective of the model is to classify patients into 4 classes: green, yellow, orange, and red. The supervised machine learning algorithm was the key nearest neighbors. Size fulfills the intended requirements. Before the training of the adherence control classification model, the data needs to be prepared to be fed to the model. Therefore, the data will go through the following steps. Pre-processing of data, where several data related to the patient are extracted from the database of the system, like age, education, and gender. Date type identification, where the type, nominal, ordinal, discrete, continuous, and logical for each variable is going to be identified. Data normalization, where every value of every variable is normalized, for instance, between 0 and 1. This step is necessary to ensure that the different variables have the same range of values, so that no variable was more influence on the result than another, making the classification model more accurate. After that, the classification model will be trained with the results variables. After the training, the classification model will be available through a RESTful endpoint that will be consumed by the application. With that, every time a new patient is registered in the healthcare system, the classification model will classify the level of the no-adherence to medication of the patient. And if the level is high, then the staff of this institution can observe that information and closely monitor that patient. The last component of our architecture is the mobile application and the administration portal. The portal of the administration and the mobile application was as main function assisting institution in the preparation and monitoring of the medication. This portal has a main functions. The registration of the new user, the real-time consultation of the medication taken that each user should take made every instance, and other functionalities. The great utility of the mobile application is to enable the collection of the data stored on the memory card added to each organizer. The collection of this data performed using Bluetooth Low Energy is only necessary in contexts where NB-IP network is very weak or inaccessible. So, last section, conclusions. This work introduces a new tool that will allow institutions that provide assistance in medication to perform a better monitoring of their users. Through rigorous control, these tools allow institutions a more agile mechanism to identify possible errors in the consumption of the medicine, contributing to increase the quality of life of your users. Thus, at this moment, the current state of the work is dependent on the elaboration of 2 or 3 prototypes of the organized present to distribute among the small group of population, and then perform tests to understand the degree of the success of the solution presently. Future work. Devise a solution to identify errors in the medication intake in the percentage of the user who do not use the medication organizer. Conduct a study to quantify the impact of the detection of the errors in medication intake with the user our solution. Append the medication stock replacement detection process. Optimize methods to detect user no adherence. Consider other machine learning algorithms and check their effect on the intelligent system of our solution.